Welcome to the deep dive. Get ready, because today we are diving headfirst into a challenge that has humbled brilliant minds for decades: predicting financial markets, specifically the notoriously tricky world of stock price movements.
Yeah, it really is the ultimate signal and the noise problem, isn't it? So many factors, all interacting in these complex ways and making consistent, reliable predictions just feels like, well, like searching for a needle in a haystack
Yeah.
during a hurricane.
Absolutely. And our source material for this deep dive is a fascinating research paper. It's titled Financial Time Series Forecasting with CNN Transformer Networks, and it comes out of JP Morgan AI Research.
Hmm.
So our mission to cut through the technical jargon and get to the core, we want to understand why this is such a difficult problem
Right.
and explore how researchers are borrowing these cutting-edge AI techniques, things from computer vision, language processing, and applying them here.
Yeah, bringing tools from other domains.
Exactly. And then discover what their innovative new combined approach actually reveals about maybe the possibility of more reliable financial forecasts.
And you'll see how bringing together these uh, seemingly disparate AI architectures can offer a really powerful new way to look at financial data,
Yeah.
potentially leading to predictions you can actually place more confidence in.
Okay, let's unpack this naughty problem first then. Why is predicting financial time series, like stock prices, why is it so notoriously hard? What's the fundamental challenge, according to this research?
Well, the paper nails the core difficulty right away. Financial data isn't simple. It has patterns, dependencies that play out over really short time frames, think immediate reactions, that kind of thing.
Right.
But it also has these complex relationships that unfold over much longer periods. And the real beast is trying to model both of those types of temporal dependencies, simultaneously.
Oh.
Most traditional methods, and even some of the newer ones, really struggle with getting that balance right.
So you've got the quick ripples, maybe from news or trading bursts, but also the slower waves of market trends or like company fundamentals. And the goal here isn't predicting the exact price down to the penny, but specifically the direction.
Precisely. Yeah, the task they're really focused on is more of a classification problem, predicting whether the price in the next step, the next minute in their case, will go up, down, or stay relatively flat. It's about forecasting the sum of your price change.
Got it. So before this paper proposed its new method, what did the landscape look like? What were the standard tools people were using for financial forecasting?
We had the classic statistical methods. The paper mentions things like um, linear regression, exponential smoothing models like EM, that's a common one,
Hmm.
and autoregressive models, things like ARIMA. These often work by trying to predict just, one step ahead. And then if you want to forecast further out, you feed that prediction back into the model recursively.
Okay. And then the world of machine learning and deep learning arrived on the scene.
Exactly. And these came along really to better handle the sheer volume and complexity of financial data, all those nonlinear relationships,
Mhm.
and also to kind of automate the process of identifying useful patterns or features directly from the data itself.
And for sequence data like time series, the common deep learning approaches were often things like recurrent neural networks or LSTMs, long short-term memory networks.
Yeah, RNNs and LSTMs, they're built for processing data sequentially.
But they had limitations when it came to this specific problem, right?
Right.
Especially the long-term stuff.
They do, yeah. While they're great for sequential data in general, RNNs and LSTMs can really struggle with capturing those long-term dependencies we talked about earlier.
Okay.
As the sequence gets longer and longer, it just becomes harder for them to effectively remember or relate information from the distant past to what's happening now. They can suffer from what's sometimes called the vanishing gradient problem, which makes it hard for the model to learn effectively from those early data points in a long sequence.
Okay, so if capturing those subtle long-term relationships across a whole sequence is a key weakness for RNNs and LSTMs, where else in the AI world have we seen models that actually excel at understanding connections over long distances?
And that's where this paper gets pretty clever. They look at breakthroughs happening in other fields. First up, convolutional neural networks, or CNNs.
From computer vision, right,
Mhm.
image
Yeah.
recognition.
Exactly. These models totally blew up in computer vision, revolutionized how we analyze images.
Because they're so good at spotting local patterns, like edges or textures in a picture.
Precisely. And for time series, a 1D CNN can work similarly. It can scan over small local windows of the price data, picking up on short-term trends or, immediate pattern sequences. They're fantastic at modeling those short-term dependencies.
But they have a limitation for the long-term problem we keep coming back to.
Yes, Their receptive field, the amount of data they see at once, is inherently limited to the size of that scanning window. They don't naturally see the big picture or relationships between points that are far apart in the sequence.
Okay, which brings us nicely to the second borrowed technique, transformers. These models basically transform the world of natural language processing, NLP.
Absolutely.
Mm.
Transformers are the backbone of so many state-of-the-art language models today. Their superpower is learning global context and those crucial long-term dependencies across an entire sequence of text, or in this case, data points.
How do they manage that long-term part so much better than, say, RNNs or LSTMs?
The key is their attention mechanism, specifically something called multi-headed self-attention.
Okay.
Instead of processing the data point by point sequentially like an RNN does, a transformer looks at the entire input sequence all at once. The attention mechanism lets it weigh the importance of every other point in the sequence when it's processing a single point, no matter how far apart they are.
Oh, okay.
So it can directly build connections across, say, the entire 80 minutes of data they used.
So it doesn't sort of forget what happened 70 minutes ago by the time it gets to minute 80. It can see that relationship directly. Okay. So given that challenge modeling, both short-term and long-term dependencies and strengths and weaknesses we just discussed for CNNs and transformers, I'm guessing the paper's core idea is to just slam them together.
You got it.
Oh.
Basically, yes. The paper introduces CTTS, CNN, and transformer-based time series modeling.
CTTS.
And the central hypothesis is exactly what you said. Combine the CNN's ability to see fine-grained, local patterns with the transformer's ability to see the global long-term structure between those patterns. The hope is they can build a model better equipped for the messy reality of financial time series.
Like getting the best of both worlds, but specifically tailored to this problem. Okay, walk us through how the CTTS method works then, step by step as they describe it.
Okay, so you start with the raw input data, the time series of stock prices. First thing, they standardize this data. They use min-max scaling, which basically puts everything in a consistent range, like 0 to 1.
Right, standard practice for a lot of ML models. Helps with training.
Exactly. Helps the model train more effectively. Then, this standardized data goes through some 1D CNN layers. Think of these CNNs as pattern detectors, sliding over small windows of the time series data.
Okay.
They process each little window and turn it into a numerical representation, what the paper calls tokens. These tokens essentially capture the short-term patterns that the CNNs identified in those local windows.
So the CNN takes the raw price squiggles and turns them into a sequence of, like, pattern pieces.
Exactly, yeah. Sequence of features representing the local dynamics. Now, here's a key step for transformers. Because transformers process everything in parallel, they don't inherently know the original order of the data. So they add positional embedding to these tokens.
Ah.
Think of it like adding a little timestamp or a sequence number to each pattern piece so the transformer knows where it came from in the original 80-minute sequence. It preserves the time ordering.
Okay, so the tokens are created, they represent local patterns,
Yeah.
and they're stamped with their original position. What happens next?
These position-aware tokens are then fed into the transformer model itself. And this is where the long-range magic happens. The transformer, using its self-attention mechanism, analyzes the relationships between all these different pattern tokens across the entire sequence. It learns the long-term dependencies and the global context from how these short-term patterns interact over time.
So the CNN identifies the local building blocks, the little motifs, and the transformer figures out how those blocks fit together over the whole history they're looking at.
Precisely. That's a great way to put it.
Yeah.
The output of the transformer is then a final compressed representation. They call it a latent embedding vector. It captures the essence of the entire process time series, informed by both those local and global patterns.
Okay.
This vector then goes into a final classification layer. It's actually quite simple, just a multi-layer perceptron in MLP with a softmax activation function at the end.
And the output of that is the prediction.
Yes. The final output is a probability distribution over the three possible outcomes. Price goes up, price goes down, or price stays relatively flat in the next minute. And those probabilities, of course, sum up to 1.
That's actually a really clean, kind of elegant way to combine those two architectures. So they built the CTRS model. How did they test if it actually works better than the existing methods? What was the setup?
Right, the crucial part. They set up an experiment using real-world, high-frequency data, specifically 1-minute interval stock prices for S&P 500 constituent stocks using data from 2019.
Okay, real market data.
Yep, and the task was exactly what we discussed. Use the first 80 minutes of price data in a window to predict the price movement up, down, or flat in the 81st minute. They used data from the first 3 quarters of 2019 for training and validation, and then the last quarter of 2019 for testing the final model.
And they compared CTTS against a few different types of baselines, right? Not just older methods.
Yes, they benchmarked it against standard traditional methods like ARIMA and EMA, which we mentioned, but also against a strong deep learning time series model called DeepR, which is based on recurrent networks. And just for sanity checking, a naive baseline that just always guesses the most frequent outcome they saw in the test data.
Okay, and how did they measure performance? What was the key metric they looked at?
The main metric was sign prediction accuracy. Basically, how often did the model's predicted direction up, down, or flat match what actually happened in that 81st minute?
Straightforward enough.
And they measured this for both a simplified two-class problem, where they grouped up and flat together versus down, and also for the full, harder three-class problem, up versus down versus flat.
And wasn't there also this interesting concept they introduced called thresholded accuracy? Tell us about that.
Ah, yes. This is where the results get particularly interesting, I think. Beyond just the overall accuracy, they also looked at performance only on the predictions where the model was most confident.
How did they define confident?
Specifically, they filtered the results to only include predictions where the probability the model assigned to its chosen class, say, up, was above the 75th percentile of all the probabilities it ever outputted during the test phase.
Okay, so only looking at the top 25% most confident predictions.
Exactly. The idea is to see if the model is more reliable when it's more certain. If accuracy jumps significantly on these high-confidence predictions, it means the model's probability outputs are actually meaningful indicators of correctness. It's not just guessing randomly with high numbers sometimes.
That makes sense. Okay, let's get to the numbers then. How did CTTS actually perform on standard accuracy against those baselines?
Okay, so on the standard two-class accuracy, CTTS came out on top at 56.7%.
Okay.
The next best was EMA, the exponential smoothing, at 53.2%. Then DeepR was at 51.1% and ARIMA at 50.9%. So CTTS is ahead.
Ahead, but maybe not a world-shattering difference there for the two-class. What about the harder three-class problem?
For the standard three-class accuracy, CTTS again led the pack with 44.1%. EMA was next at 39.5%. Then ARIMA was 37.5%, and DeepR was very close at 37.4%. And just for context, that naive baseline just guessing up all the time because it was the most frequent class in their test set would get about 37.1%.
So CTTS is definitely better than guessing and better than the other models, but maybe 44% doesn't sound amazing on its own in a world where random guessing is 33.3% for three classes.
Right, exactly. The overall accuracy shows an improvement, but it's not like it's predicting perfectly. However, this is where those thresholded results tell a really different story.
Okay, so what happened when they only looked at those high confidence predictions?
This is where the paper highlights what they call a significant gap. When looking only at those predictions above the 75th percentile confidence threshold, the accuracy jumped for all the models, which you'd kind of hope for.
Right.
But the gain in accuracy and the absolute level of accuracy on these more reliable predictions were notably higher for CTTS.
How big was that difference? Can you give us the numbers?
Yeah, for that thresholded three-class accuracy, CTTS hit 55.2%. That's a pretty big jump from its standard 44.1%.
Wow. Okay.
Now, compare that to the baseline's thresholded accuracies. EMA only got to 41.7%, ARIMA was down at 38.4%, and DeepR was 38.7%.
So CTTS at 55.2% versus the next best, EMA, at around 41.7%. That's a roughly 13-14 percentage point lead for CTTS, but only when looking at the predictions where the model itself is most confident.
Exactly. That gap in the thresholded results is really quite telling.
What does that strongly suggest about the CTTS model compared to the others then? What's the implication?
It strongly suggests that the predicted probabilities generated by CTTS are much more, well, reliable, seems like the right word, compared to those from the other methods. Meaning when the CTTS model assigns a high probability to a specific direction, up, down, or flat, it's significantly more likely to actually be correct than the other models are, even when they are expressing high confidence. So you can use the model's own confidence level as a pretty good filter. If you focus only on the high confidence predictions from CTTS, you get much higher accuracy. This reliability likely stems from its better ability, that combination of CNN and transformer, to capture both the local and global patterns effectively, leading to predictions that are more informed and therefore less uncertain when it is certain.
Okay, so stepping back, what does this all mean for the bigger picture? What are the potential implications of developing a model that can provide these reliable probabilities for price movements, even if the overall, average accuracy isn't perfect yet?
Well, that reliable probability is really the key, I think. It connects this technical improvement directly to potential real-world application, particularly in downstream trading decisions.
Ah, so actually using these predictions to inform whether someone or something should buy, sell, or hold a stock.
Exactly. The paper explicitly suggests that this reliable probability output enables more sophisticated trading strategies than just acting on every single prediction. A very simple approach would be, buy if predicted up, sell as predicted down, hold as predicted flat.
But the reliability of the probabilities allows for more nuance than just that.
Yes. Because the higher probabilities are demonstrably more likely to be correct for CTTS, you could potentially factor that confidence level directly into your trading decision.
How so?
Well, for example, the amount of shares you decide to buy or sell might scale with the model's predicted probability for that direction. A very high confidence up prediction might trigger a larger buy order than a prediction that's only just slightly above the threshold for up.
That makes intuitive sense, essentially. Bet bigger when the model is more sure of itself, and maybe hold back or bet smaller when it's less certain. Okay, bringing it all together then. The core takeaway from this deep dive seems to be that researchers have made some meaningful progress in tackling this really complex problem of financial time series forecasting. They did it by cleverly combining the strengths of CNNs for local pattern spotting and transformers for long-range dependencies into this method they call CTTS.
Right. And the critical finding isn't just that modest gain in overall accuracy, which is nice, but really the demonstration that this combined model produces surprisingly reliable probability outputs. Its own confidence level seems to be a strong indicator of correctness.
Which is crucial.
It's crucial for bridging that gap between a research model on paper and potential real-world applications like building more robust, maybe more risk-aware automated trading strategies.
Yeah, and that ability to generate reliable probabilities for something as seemingly chaotic as intraday stock movements, that feels like the truly significant step forward here. It really leaves you, the listener, with a compelling question to think about. How might trading strategies evolve if you can systematically incorporate a reliable confidence score into every potential trade? How could you potentially leverage those high probability signals to better manage risk and maybe capture opportunity? That's definitely something to mull over long after this deep dive wraps up.